Okay, this is the third video in the series of trees. In this one, I would like to discuss ordered binary search trees. Now, ordered binary search tree, or short just a binary search tree, and we use this BST acronym, is still a binary tree in that every node has two children, or max two children, 0, 1, or 2 children. But there's a difference in that the nodes are ordered. In the previous example, the nodes were in no specific order, but in this case, the nodes are ordered. If now we take our vertical line and we slide this vertical line from left to right across the tree, you will see that the nodes are ordered 7, 11, 13, 16, 17, and 19, 23, 35. And once again, my 17 should be written, typed to the left of the root. It's the visualization that's wrong. It's not the tree that's wrong. So this is in order. Sliding this from left to right is in order. And the whole idea of a binary search tree is to provide nodes in an ordered way. So this will mean that the class user will not now take responsibility for adding nodes. In previous cases, we said, all right, let's create all the nodes first as separate trees, and then afterward the class user must then link them in the way that the class user wants them to be linked. In this case, no, we do not do that. The class user does not take responsibility for linking the nodes. The tree itself must take responsibility for linking of the nodes so that the nodes are linked in order eventually. So this is, again, the way in which we are doing it with the members. This is exactly the same as for a binary tree. We added the parent member here, but that is not necessary. That is only necessary if we want to make provision for removal of a node. If you do not foresee the possibility of removal of a node, we do not need the parent field here. We can just stick with what we had previously, the value itself, and then the left and right trees. I'm going to skip paragraph 5.2. That is the implementation of Nykov. It's alternative. I do not want to confuse you, so let's just skip that one. If I have a value in a binary search tree and I need to find it, there's a specific way to go through the procedure. Let's say I want to determine if a tree contains a node. So let me put this thing again to the side here. And then my picture, sorry, the implementation, the Visual Studio part. No, sorry, that's not what I want to do. I'm sorry, this is not what I want to do. I want to split. Oh, I can do this. And then, sorry, this is not professional, but it's not intended to be professional video recording. I want to have the picture there, and let's put the Visual Studio implementation on this side. And then let's do the traversal here. Where's my searching? There, that's what I need. All right, that's what I need. So if I want to determine if my specific tree has a value, so let's say I want to find and make sure that 13 is in the tree, then I will need a method contains, and the class user will send through a value, in this example case 13. This method will be public because the class user should be able to call it. It will return a bool, either true or false. Then this method in turn will call this find method, which is private in the class. Only the class itself has access to it. This is not recursive. That's the very first thing that we need to see. This is not recursive. We are running in a loop. So there's a loop, not recursive. Now what we have to do is to start from the root, 19, and compare the value that we are looking for with this first starting entry point. So 13 is less than 19. That means we go left. Remember, this is an ordered tree, so things are in order. The left subtree is less than the right subtree. All elements in the left subtree is less than the root, and all elements in the right subtree is larger than the root. That's the whole idea of a binary search tree. So if I start with 13, compare 19, it's less, go left. Compare 11, it's larger, go right. Compare 16, it's less, go left. Ah, I got it. So this is the way that we will search for a value. Starting from the root, go left, right as necessary. So since we are working with a generic class, I cannot use an equal sign. I need to use this compare to method, which says, all right, compare this value with that one. And this compare to method, and we've encountered this one before, will return an int, and that int will be limited to one of three values, either -1, 0, or +1. -1 if this one is less than that one, equal, 0 if this one is equal to that one, and +1 if this one is larger than that one. So use the compare to method, and then take that int that it returns, put it into a temporary variable. If that thing is less than 0, meaning -1, we go left. If it's larger than 0, we go right. And if it is equal to 0, we break, means we found what we needed. So this node is our temporary placeholder. We kick off with the root. And then as we go left or right, we replace this node with either the left child or the right child. And that's all that there is to this find method in a binary search tree. The break means break out of the loop. So this loop will be terminated under two conditions. First of all, the loop will be terminated when the node is null, because we cannot carry on if the node that we're currently working with is null. And secondly, it will be terminated when we found the thing that we was looking for. Let's say we take an example from this tree on the left-hand side, where we are looking for, let's say we look for 15. So compare 15 with 19, it's less, go left. Compare 15 with 11, it's larger than, go right. Compare 15 with 16, it's less, go left. Compare 15 with 13, it's larger, go right. Oh, there is nothing there. So there is no right child. So that means we reached the end of the tree and we never found it. So that will then be this condition there. The left child and the right child will now be null. So nothing to compare with, and we will return a null there because there is no such child. So this is the way in which we step through and find a value in an ordered binary search tree. So it's not by traversing the tree in the previous way and then we stop when we found. We traverse in a very specific way, either go left and right. Now this is efficient. I think I played this game with you several times in the past. If I think of a number between 0 and 100 and you have to guess that number, you have to make an intelligent guess. So you guess 50, that's halfway, and I will tell you you are too low or too high. And then you will, let's say that will be too low, and you will then guess, split the remaining. So you will now guess 75, which is halfway between 50 and 100. I will tell you that's too high, and that will mean that you will now split the interval between 50 and 75 into 2, 67, and you will get 67. I will tell you it's too low, etc., until you get to the correct number. Now, if you do this, you will always reach the value that you need within log n base 2 guesses. So if n is 100 and we work with base 2, then 2 to the power of 7 is 128. So you will never need more than 6 guesses. If I think of a number between 0 and 1,000, now 2 to the power of 10 is 1024. So you will never need more than 10 guesses to get to your number that you need. So a binary tree, or a binary search tree rather, has this advantage that searches can be very efficient. Searches can be very efficient. But there's a condition. The tree has to be set up properly. If we enter the values and the values are originally in a sorted order. There. If I enter the values and the values are originally in sorted order, then the values in the tree are entered like this, and I actually have a linear structure. I no longer has a tree. This is an unbalanced tree, and I lose the advantage of searching for a value if my tree looks like this, if my tree is unbalanced. So we need to make sure that the tree is shallow but broad, and then a binary search tree will be very efficient. So that was the find procedure. Now, if I traverse a binary search tree, the whole idea of a binary search tree is to carry values in order. So all my traversal methods in the previous case are actually now unnecessary. I can remove all the other traversal methods and only stick with the in-order strategy. That's all that I need. So all the other traversal strategies in binary trees can be thrown out, and we just keep the in-order strategy because that is the whole purpose of a binary search tree. Now, the important thing is the addition of a node into a binary search tree, and that is, you will remember that I said that the tree itself will now cater for linking the nodes. No longer will the class user link the nodes. So when I add a value, I simply tell the tree to add a value. Let's go to the class user here. So I create my tree with an initial root value. This is my example case here. And then all that I need to do is to add the values, and I can add them in any order. The tree will take care of the addition itself. So what if we look at the example? Let's say I want to add the value 16 to this tree. So I already have a 19. Compare the 16 with 19 is less, so go left. I already have an 11, so the 16 compares with 11 is larger, go right. There is no right child to 11, and I will put my right child there. So I will always add a node as a leaf. It will always be added to the bottom of the tree. Never will it be inserted somewhere in the middle. Let's say I want to put a 15, and I want to add a 15 to this tree. So 15 compared to 19, go left. Compared to 11, go right. Compared to 16, go left. Compared to 13, go right. And my 15 will go there as a right child to 13. My children will always be added as leaves. Now, that has this interesting result or interesting consequence, that the order of addition of nodes will determine the shape of the tree. So here I have a set of nodes, and here I have a set of values, exactly the same set of values. Exactly the same set of values, but in two different orders. And this will now result in two different trees. So if I start with 19, will be the root, 11 will be less than, 35 will be larger than, 23 will go there, 7 will go there, 16 will go there, 17 will go there, and 13 will go there. But if I start with 16, then 16 will be the root, 23 will go there, 17 will go there. So you can follow the sequence of this values yourself and see how they are entered in a different order into my tree, so that the tree now looks differently. And that's why I say, if I take again the same set of values, and they are originally in a sorted order, I end up with a linear structure. So for a binary search tree, it's important that our tree or the initial values are unsorted. If the initial values are sorted, I end up in a bad tree. So to have a good tree, my initial values should be as in a random sorted order. That is very important. So let's go to the algorithm of this addition. Let's go to the tree first, and then take the algorithm on this side. Algorithm on this side for adding. All right, insert's actually a wrong word. It should be add, because we don't insert. Insert means put something somewhere in the middle, and that's not what we do. We add nodes by adding them to the bottom of the tree as a leaf. So we have a public version and a private version. And this is not recursive. So the public one just calls the private one, but with the current root. So this child parameter in my private version comes from there. The value is taken through all the way. So let's just make more space so that we can see everything in here. So in comes my value. If it's null, I add that to the current child. Now that's the whole idea. I can only add a child as a leaf. I cannot add a child somewhere else, so I cannot insert somewhere in the middle. So the whole idea is to step through the tree from top to bottom until I find a null, a left child or right child that does not exist. And then only I can now replace my null value with a value. So the previous null value, left child or right child of an existing node, will now be replaced with something new. So my previous node will now have a child which it did not have before. If that was not the case, I do the same thing as I did with the searching. Use the compare to method, see if I have to go left or right. And if I have to go left, the current value that I'm going to compare with my new value will be the current one, left child, etc., etc. This is only optional. You can take this out. The only idea of this is you can add a breakpoint there and then follow the logic to see when you reach there. But once we reach a null value, in other words, compared to is neither larger than 0 nor sorry, I am now confusing myself. This idea here is, sorry, I am totally confusing myself now. So this idea is something different. I will get to it now. So if I reach the bottom, I will means I have no child, and I will then assign a new value instead of the no child. The question is, what do we do with duplicates? And that depends on the problem scenario. In some cases, we do allow duplicates, and in other cases, we do not allow duplicates. And if we allow a duplicate, will that duplicate now go to the left or the right? So it depends on your scenario. In this case, we do not allow duplicates at all because that's a less than and that's a larger than. If we have an equals, we can now say, all right, go less and equal or go larger and equal. And that will then either put this new value to the left of the current one if it's less or equal, or right if it's equal to the current one. So it's important to understand that in a binary tree, we normally do not allow duplicates, but in some special cases, we may allow duplicate values. That is the add method. If you do not understand this, you'll just have to learn about it, because you have to do this. You have to be able to add values to a binary tree. If you don't understand it, go learn it. Maybe you have to, if you understand the basics of it, but you can't remember some of the smaller details like line 109 or line 112, you just learn those. All right. If we have to make provision for removal of a node, we can have another add method. So this one has 2 parameters. This one has 3 parameters. And I've commented this one out because at the moment I do not make provision for removal of a node. But if I want to make provision for the removal of nodes, I have another add method with 3 parameters there, which will also indicate the parent, and then you can go through this method yourself and try to understand it, what it does now to keep track of the parent of every node. To remove an element, I say it's not for test or exam. I will just quickly say why we can skip this one. If I look at this specific example, if I remove a node, let's say I want to remove 11, it's not a simple matter of reconnecting the children, because we might lose the ordered nature of the tree. it's important that we do not lose the ordered nature of a tree when removal and a specific node. So down here I have an example. Let's say I want to remove 11. The correct way of doing it will then look like this. 7 will go in the place of 11 and 16 will stay where it is. And there's a specific algorithm to do that, to keep the original ordered structure and don't lose the ordered nature of my tree. So this algorithm is maybe one of the few where the method is longer than 10 lines of code. In this case, how many long? About 20 if I just look at it quickly. So as I mentioned before, if your method is longer than 10 lines, and with that I exclude braces and open spaces, then you're probably going wrong. Don't try to overcomplicate things and do a lot of work. Just think of it smartly and do the work as needed. All right, so that is my binary search tree. Let me just check that I did not miss something. Yeah, auto balancing trees. There are algorithms, again, not for test or exam. If I have now a tree like this, there's an algorithm to take this tree and realign it so that it is shallow, so that it is balanced, because a balanced tree is what I need. And there are several algorithms out there. We refer to AVL trees and red-black trees, or specific ways of creating a tree so that it is balanced all the time, irrespective of the order in which we add the nodes. You can calculate the balance factor with a formula like that, but you can read that for yourself. That is for enrichment purposes. I think that is my discussion on the revision of trees.